Good morning. The last few lectures we have been looking at the displacement method for analyzing structures. Now today what we will start off with is actually looking at a method that is much older than the displacement method that I talked to you about. This is called the moment distribution method. The problem with the displacement method is that for it to be usable by hand, you can't really go beyond 2 or 3 degrees of freedom, because by hand to solve very large simultaneous equations is reasonably difficult. So nowadays, of course, what do? We use the computer, okay, to solve the problem. And in fact, after I have gone through this part, I am going to go into the matrix methods, which are essentially formulations that are very computer friendly. However, I would also like you to understand the moment distribution method, because this is a method by which you can actually analyze very large structures with lots of degrees of freedom without recourse to a computer. In fact, till the advent of computers in the 90s, moment distribution was the method that was used extensively by designers to actually analyze structures to find out the forces for which they have to design. So that is the reason why, and of course the relevance of moment distribution method today has gone down. However, it still is a very quick method by which you can check by hand as to whether your computer simulations are giving you reasonably accurate results. So that's the reason why the next few lectures I am going to talk about the moment distribution method and solve examples which illustrate how the moment distribution method is used for analyzing beams and frames. The moment distribution method is essentially a method which is used for beams and frames. Okay, so let us have a look at the moment distribution method. It is a class of iterative methods which don't actually develop all the equilibrium equations. In fact, that is the advantage of this approach, because since you do not develop all the equations, you don't have to work with a very large number of equations at one time. Okay, so let us see how that works. And for that, I am going to actually take a problem that I have already discussed earlier. This is the beam problem. Do you remember that this is 10 meter spans, okay, fixed at A, B. I'm going to call this A, this is B, and this is C. Okay, each 10 meters long. This one has a 120 kilonewton at 4 meters, and over BC you have 50 kilonewton meter uniformly distributed load. There are two equations. One is summation moments equal to 0 and summation moment C equal to 0. These two equations, we've already got these two equations. So I'm not going into the details of how we have obtained it. We've already obtained it. Please look back. You will see that these are the equations. Now, since both are 10 meters, I'm going to define I upon L, which is I upon 10, to be K. There's a reason why I'm doing this. It will soon become obvious to you. So if I do this, then these equations can be written in this fashion. The first equation I'm going to write by writing theta B in terms of the moment and theta C, and the second equation I'm going to write down theta C in terms of theta B. Okay. Now you may ask, why are we doing this? Well, bear with me. So essentially when you do this, this becomes Ek theta B is equal to 37.7 minus 0.25 Ek theta C, and EKC is minus 104 minus 0.5 EKB, theta B. Okay, so now these two equations I am going to solve iteratively. How am I going to solve iteratively? Well, initially I will assume that theta C is equal to 0. Okay, so I will assume that theta C, Ek theta C is 0. If Ek theta C is 0, that means Ek theta B will be 37.7. Okay, so now this value of EKB I am going to substitute here and find out the theta C value. Then that's the first cycle. The next cycle I found this, plug that in here, get this. So you see how iteratively I'm looking at it. If you look at this is how it looks, the iterative solution. Okay, initially step 1, assumed value of theta C is 0, so there is no. From that you can find out it's 37.7. Now in the second step you take 37.7, find out Ek. Then third step, use this, put it in the first equation, get this. The next step, use this, get this. You understand the way this is being solved? The way this is being solved is that first I start off, my first step, I am assuming theta C to be 0. Then I can find out theta B. Once I find out theta B, second step, I plug in that value of Ek theta B here to get Ek theta C. Once I get that, the third step, I plug this in here and keep doing this. And it can be shown, problem with this is that you have to understand that this iteration has to converge. Okay, if it doesn't converge, then you are not really, it's not useful. It can be shown mathematically that you can show that this converges, and I will show you the details of this method here. Okay, so if you look at this, Ek theta C theta B, then put the value of theta B, you get theta C. Okay, keep putting that in. Then see every step, first step 0, then you evaluate theta B, then you put that into theta C, get theta C. Then you put that Ek theta C assumed value and solve for E theta B. Then you use that value of Ek theta B and solve for Ek theta C. Then you use that, then you get. Okay, continue that way, see what happens. Assume a value of Ek theta C, get Ek theta B. Then you assume that value of Ek theta B, you get the value of Ek theta C. You assume that value of E theta C, you get back the original value. What does that mean? That means that the two equations have given you the same solution, it has converged. Okay, and so therefore ultimately the values of Ek theta C are this and Ek theta B is this. Okay. So this is a standard iteration procedure known as the gaussseidel iterative procedure. Okay, and gaussseidel iterative procedure can be shown that this will always converge. Okay. So therefore let us go back and look at what this implies by looking at what effect does this. Of course, once you've got this, you can plug in these values into MAB, MBA, etc. and get it. However, moment distribution is not the Gauss-Seidel iteration procedure. Let us look at what this implies in terms of the moments themselves. Okay, see, note that Ek theta B, Ek theta C, we evaluate not because we want to find out what the value of theta B and theta C is. Understand that very rarely are we interested in what the rotations are. We are interested in calculating the rotations so that we can calculate the moments. So now let us see what these moments actually look like. Okay, so if you look at it, the equations come out this way. This is for the same equation. MAB is equal to 2 into Ek theta B minus, this is, I am just rewriting what we had already written, accepting that this k is I upon 10. MBA is equal to 4 into Ek theta B plus 115.2 MBC is equal to 4. I'm sorry, this is this and this is negative 4 ek theta b plus 2 ek theta c plus 416 and mcb is equal to 4 ek theta c plus 2 ak theta b minus 416.7. Okay, these are of course this as positive. I have taken anti-clockwise as positive. Okay, so these were the expressions for MAB, and then you had the two equilibrium equations, one which said that MBA plus MBC is equal to 0, and the other one which said MCB is equal to 0. Okay, so these were the equations that we had written down earlier, and I'm just going through that. Okay, so now let us see what actually happens in this particular. MBA plus MBC is what gives me this equation, and MCB equal to 0 is what gives me this equation. You can look at it. Okay, so this one here is actually plus and minus. Okay, so this is minus and this is plus. Plus minus. Okay, so now if I look at it, let us see what these mean, and I'm going to write down this iterative solution that I've written down, excepting that I'm going to write down the values of MAB and MBA. So if we look at it, if we look at the moments, okay, and I'm going to draw again. So first one is step number, then I'm going to write down ek theta b, ek theta c. Both the, in this step, if for example in the initial step ek theta c is taken to be 0 and ek theta b is also taken to be 0, right? So right in the beginning, that's the first. Then we plug in ek theta c. Let's see what happens to MAB, MBA, MBC and MCB. Okay, so MAB when it's 0, 0 is going to land up being 172.8. This is going to be minus 115.2. This is going to be plus 416.7, and this is going to be minus 416.7. So these are the moments when I take theta. Then we have the first step. The first step, what did we say? That we took this equal to 0, and so therefore this became minus 37.7. Okay, so if this becomes minus 37.7, if we plug that in, we plug it into now all of them. So I'm putting theta b equal to minus 37.7 and theta c is equal to 0. So I can compute. So when I compute these, what I get is this becomes 97.4. This becomes minus 266. This becomes plus 265.9, and this becomes minus 492.1. If you look at this, I'm going to now look at this. When I when I substitute and I get the value of theta b, what I'm actually doing is releasing, this is both the joint at B and the joint at C clamped. Okay, so when they are clamped, these are the fixed end moments. Okay, then what am I doing? I'm actually keeping theta C clamped, okay, and releasing the clamp at B so that theta B can occur, so that when I release the clamp at B, what happens? MBA plus MBC has to be equal to 0. So for all practical purposes, this is equal to 0 if you look at it. Okay, so that's what I have done. Okay, so I have actually released it and made it equal to 0. However, MCB is not equal to 0. Okay, so next what do I do? The second step, I clamp B at the rotated position and release theta C. So when I release theta C, what do I get theta C to be equal to? It becomes plus 123.1. So now if I plug this in and compute, this remains the same because this is not affected by theta C. Okay, this remains the same because this is not affected by theta C. But this changes because it's affected. This becomes plus 512.1, and this becomes plus 0.0. What have I done? I have actually kept theta B and released theta C. As soon as I release theta C, what happens to MCB? Right? It has to be equal to 0. That's what you get. So you see how now the third step is what? I keep theta C clamped at that position and further release theta B. So when I release theta B, I get that equal to minus. Note that this is exactly the numbers that I had over here, excepting that I just made one mistake. I took clockwise as positive. So this is, bear with me, this is anti-clockwise. My anti-clockwise is positive. So okay, so the first step, this, second step was this, third step is 123 minus 68.5, that's what I have over here. Okay, so I've clamped it here, released it here. When I've released it here, what does my value become? It becomes 35.8, and this now becomes minus 389.0, okay, and plus 389.0. However, this becomes, if you look at it, this becomes plus 61.3. So what we've done is, as soon as we release theta B, again this balances out. So actually, if you look at this, now I'm going to just write down all the subsequent ones which we have computed, that you take this as this and compute this. So this becomes plus 138.5. I'm going to write down the ones that we've already got. This is plus 138.5, and you get minus 72.3. Then the sixth step is take minus 72.3 and you get plus 140 by 4. Seventh step is take 140 by 4 and you get minus 72 by 8. Eighth step is take 72 by 8 and you get 140.6. And if a ninth step is identical because you get the same value. Okay, so this is the converged value, and for each one of those you substitute theta b and theta c, and I'll just write down the values that you get. You get 35.8, 28.2, 28.2, 27.2, 27.2. This one you get as minus 389.0. Then you get plus 404. Then you get plus 404. Then you get plus 406.4 plus 406.4. Here you get minus 419.7. Here you get minus 400.5. Here you get minus 408.3. Here you get minus, plus 406.3, and here you get plus 406.7. Here 61.3 you get plus 0.1. So this is you're releasing this. Then the next one you're releasing this, and so you get plus, I'm so sorry, here you get minus, here you get minus 7.3, here you get plus 0.1. This is the one that you're taking to 0. Okay, then you get minus 0.7. This is where you release B, theta B. So alternately you're releasing theta B, theta C. Okay, and finally you have plus 0.1, which is the release. This should actually go to 0, but we have a least square. Now, this is the solution that you have. The procedure, if you look at it, what we can say out what the procedure is. The procedure is you start with both B and C clamped. So you clamp B and C. So what are your moments at AB, BA, BC and CB? They are the fixed end moments. Okay, so you know what those are. So the first step is that you keep theta C clamped. So that means Ek theta C is 0, and release the clamp at B. Immediately as soon as you release the clamp at B, what happens? The net unbalanced moment, see there is a net unbalanced moment because of the fixed end, that moment gets distributed. It gets distributed on both sides, and here what you have is balance of moments here, but that leads to an unbalanced moment here. When you release this, you get Ek theta C as this, then immediately you have this going to 0 because you've released the clamp at C. So the moment at C has to go to 0. Okay? But that creates an unbalanced here. So now you distribute those moments. Okay? So when you distribute those moments, it creates an unbalanced again here. So you understand the point. What you are doing essentially is clamping, releasing, clamping, releasing, clamping, releasing. So the whole procedure that you have over here is essentially a whole set of clamping and releasing. Physically clamped, release theta B, clamp theta C. Clamp theta B at the rotated position, release theta C. Clamp theta C at the released position, rotated position, release theta b. Keep doing that till you have a situation where even when you release, you essentially get the same thing, which basically means that you have balanced forces here and you have balance here. So therefore, these are no longer clamped because you have released, and this is the final member end bending moments. Okay? So these are the final member end bending moments, and this in essence, what are you doing? You are distributing moments. So this in essence is the background behind the moment distribution method. So although we looked at it, it was a gaussseidel, this is the gaussseidel iterative procedure. When we look at it in terms of m's, what do we get? We see that it is essentially distributing unbalanced moments at all times and ultimately getting to a situation where all moments are, there is no subsequent distribution because all moments are balanced where they are supposed to be balanced. Note that here you have unbalanced because it's a fixed end. A fixed end can take a moment, whereas you cannot have an unbalanced moment at B and you cannot have an unbalanced moment at C. Okay? So now with this background, let us try to see what the method actually is. Okay? So let us go through these steps. I'll just finish off putting this together, and we will put down what the moment distribution method actually looks like. It actually is a moment distribution. So we are not going to do the gauss-seidel. We've just introduced the gauss-seidel iterative procedure to show you physically what the moment distribution method does. Okay? So essentially, let us look at this situation. You have a situation where when you clamp it, you have MBA. This is the not the final moment. So you've got at a particular step, you look at MBA plus MBC and you get a net moment. Okay, this is the unbalanced moment. When you add, this should be 0. So this is the net unbalanced moment. This is the okay. So if this is the net unbalanced moment, when we release this, what do we get? We get Ek theta b is equal to minus mb, because when we add this plus this is the procedure. I am writing down what the procedure is. So you unbalance. So this is what does balancing this moment do then? What it does is the new MBA turns out to be equal to Ek theta b No, I'm sorry, I'm making a mistake here. This will be some n times Ek theta b, because that is the net unbalanced moment that we have. So you get it is equal to whatever this one is, n1 Ek theta b plus mba, and mbc is equal to n2 Ek theta b plus mbc. So these are the new. Okay? And if we look at it, what are n1 and n2? Okay, n1 and n2 are the numbers, and you will see here, since we are doing mba plus mbc, that n1 plus n2 is equal to n. . because it's this plus this. So if you now look at this, what do we get? This plus this is equal to this plus this. So if you look at this, n1 plus n2 is equal to n, but this is equal to minus, and this plus this is equal to mb. So what you get is mba plus mbc is equal to 0, balanced. So we have released theta b to get a balance. And so therefore, what is the distribution factor if you look at it? We will see that this n1, what is this n1? If we look back, we will see that this n1 is equal to 4. What is n2? You will see that n2 also is equal to 4. Okay? So n1 plus n2 is equal to 8. In fact, we know n is equal to 8. Okay? So now we get to a kind of a situation. So although this is the procedure, what we are really doing is we are not doing this procedure. What we are actually doing is taking the unbalanced moment. So we have a situation where we have the unbalanced moment. So we have an unbalanced moment. Okay? We take minus mb. Okay? And distribute this moment to BA and BC. How do we distribute this? This will get distributed exactly. Let us see what do we get. See, EK theta B is equal to minus MB upon N. Right? So how much are we adding? We are adding N1 EK theta B to BA. So what is that equal to? That is equal to, you will see, minus N1 upon N of MB. Okay? So to B, we actually apply minus N1 upon N MB, and here we apply minus N2 upon N MB. So if you look at this, this is minus comes here actually. So minus comes here. So if you look at these, what are these? These are the independent factors that you have. So we can now say that MBA, this is the distribution factor. So the distribution factor is this way. We'll call it the distribution factor to I is equal to Ni upon summation Ni of all the members coming at the joints. Okay? And what is Ni? If you look at it, you will see that this will be essentially equal to, since both N1 and N2 are 4, you will see that this essentially turns out to be equal to Ki upon summation Ki, where Ki is equal to I upon L of the ith member. Okay? So therefore, we can see that essentially you get that every time, so this one is my, I'll call this as my KBA, this I will call as my KBC, and so therefore distribution BA is equal to KBA. Remember K is equal to I upon L. Remember that? So KA plus KBC, is equal to KBA upon KBA plus KBC. And the distribution factor for BC is equal to KBC upon KBA plus KBC. So the first step is finding out the distribution factors required to distribute the unbalanced moment to the individuals. Now there is another step. So this step, if you look at it, is essentially releasing theta B. But understand one thing, that as soon as I release theta B, let's see what happens to MBA. See, MBA is equal to 4 EK theta B plus fixed end moment. BA. What is MAB? 2. Now the unbalanced moment, when we release theta B, what do we get? This term comes in. So as soon as we release theta B, what happens? So this is the unbalanced moment we have distributed to BA. But what is the additional moment at MAB? MAB is equal to 2 EK upon theta B. So when we do the balancing, what do we get? Okay, if you look at this, that this additional moment that we apply to MBA due to the unbalanced is equal to 4 EK theta B, but delta MAB is equal to 2 AK. Okay, so therefore delta theta B, which is the net, this thing. So if you look at it, delta MAB upon delta BA is equal to 2 EK theta B delta B upon 4 EK delta theta B, which is equal to half. So in addition, as soon as you have the distribution of the moments, you also have to carry over this distributed moment to get the, and what is the carryover factor? It is half. Now this carryover is half if you whether you apply at AB or whether you apply at BA, because you will always see that if you have MAB is equal to 4 EK theta AB plus 2 EK theta BA, MBA is equal to 2 EK theta AB plus 4 EK theta BA. So if you look at this way, if you release theta AB, you need to carry over to MBA, which is half, and when you release theta BA, you need to distribute. So half is the carryover from any clamped end when we release the clamped end. Okay, so that is known as the carryover factor. Okay, so this is the carryover factor, and for a uniform beam, this happens to be equal to half. Okay, now note that if you transfer a moment to a fixed end, remember that you do not release a fixed end. So there is no carryover from the fixed end to the other end. Okay, it is only when you release do you generate this carryover. Okay, so now having put this in, let us see how we solve this particular problem, the problem that I had defined, how we are going to solve this particular problem using the moment distribution method. So let us now go back and I will show you that exactly the same steps are being followed, excepting that explicitly nowhere do we actually compute Okay, so this is the structure. Now I know what the fixed end moments at AB, fixed end moment at AB is equal to plus 172.8 kilonewton meter, which basically means this positive, so this is this way. Then fixed end moment at BA is equal to minus. So the first thing that we do is compute the fixed end moments. Fixed end moment at BC is equal to plus 416 kilonewton meter, and fixed end moment at CB is equal to minus 416.7. So I calculate first of the fixed end moment for each member AB and BC. This is for member AB and this is for member BC. So I have calculated the member. What is the next step? The next step is to compute the distribution factors and the distribution factors and the carryover factors. So distribution factor, we have member B and member C. So distribution factor for BA at B, this is at B, distribution factor is going to be equal to I by 10 upon I by 10 plus I by 10, which is for BC. So this becomes equal to half. dBC is equal to I by 10 upon I by 10 plus I by 10, which is equal to half. Now carryover factor from B to A is equal to half. Carryover factor from A to B is 0. Why? Because A is a fixed end. Carryover factor from B to C is half. Carryover factor from C to B is half. Okay. At C, distribution factor CB is 1 because there is no other member at that point. Okay. So we've calculated the distribution factors, and now I'm going to put this all in a table. I have AB, BA. This is member AB, and now for member BC, I have BC and CB. Okay. Now here there is no distribution, so there is no distribution. Here the distribution, we've just calculated the distribution factor 0.5, half. Here the distribution factor is 1.0. This way carryover factor is half. This way carryover factor 0. This way the carryover factor is half. This way the carryover factor is half. So now let us start the procedure. The first step is writing down the fixed end moments. So this is plus 1 72.8. Then we have minus 115.2 plus 416.7 minus 416.7. So the first step is calculating the unbalanced moment here. What is the unbalanced moment over here? 301.5. So that one has to be distributed. How do we distribute it? Half, half. Now note, it's plus, unbalanced moment is plus 301. So the distributed moment has to be minus 301. So it is minus 301 which is being distributed. So if you look at it, what is the distribution? Half, half will become 301.5 will become, I can say 150.8. So I'll put 150.8 here. And I'll put minus 150.8 here. Okay. Now, having done that, so I actually put here. What does this mean? This means that I've completed the distribution. And if you add these up, what do you get? Plus, so it's both sides is negative. What do you get? Add them up. Just satisfy yourself. You'll get 266.0 and this side you will get 265.9. Do you see something? And now note, I will have to carry over these, because as soon as I release this, I have to carry over here. Carry over is half. So what do I get? Minus 75.4. Here I have to carry over half. So I get minus 75.4. Okay. So if you look at it, what do you get? Add these up. You will get, let us go back to the old one that I had shown. I'm not adding them up, but I'm just showing you that if you look at this, 97.4, add these two up, you'll get 97.4. Add these two up, you'll get minus 266. Add these two up, you'll get 265.9. Add these two up, you'll get 429.1. So you see the point that I'm trying to make, but note that here we are not talking about releasing. All that we are doing is distributing moments. Okay. So now if we look at it, what's the next step? The next step is like this has to be equal to 0. So I have to add 492.1. That way, this now if you add up, you will see that it adds up to 0. Okay. But for that, as soon as I release this, this has to carry over here, and so this will become plus 246.0. Okay. Now this is an unbalanced, because note that see here there is no question of unbalanced because this is a fixed end. So you do not require any, when you have a fixed end, you do not require any release. Okay. This is what needs to be, you cannot have an unbalanced moment here and an unbalanced moment here. Now as soon as you release this, you've got this. So now you need to distribute this. So distribute it half half. So what do you get? You get minus 123.0 minus 23.0. Okay. So that balances it out. But this causes this to go here and this to go here. So this becomes minus 61.5. This becomes minus 61.5. Now because of this, you need to do plus 61.5. Here if you get, this becomes plus 30.8. So now you need to balance this. You balance this. You need to balance this. So what you get? You get minus 15.4 minus 15.4. This is balanced, but this is going to lead to, again, carry over here. So minus 7.7 minus 7.7. This gives to an unbalanced here, plus 7. So this now carries over here, plus 3.8. See, when you get unbalanced here, you require minus 1.9. Minus 1.9. Again, balance minus 0.9, and here you get minus 0.9. This way you continue, okay, till you get 0, 0, and then what do you get as the final value? The final value you get as which we got here. And at every intermediate step, if you add them up, you will see that you will get this. So actually the moment distribution method mimics this. Only thing is that in the moment distribution method, all we are doing is computing unbalanced moments, distributing it, carrying it over, distributing it, carrying it over, distributing it, carrying it over. Okay? So the moment distribution method, the physics behind the moment distribution method actually is you are calculating. What you are doing is initially clamped. Okay, for this particular problem, there are two joints which are clamped. You calculate the fixed end moments. Then you release theta b. Okay, so that you get a no net moment at B, and so MBA plus MBC is equal to 0. Okay, next, what do? Release theta c. When you release theta c and you hold theta b here, what do you get? You will end up getting an unbalanced moment at this point. So now you release it furthermore. Okay, then you release this, till you get to a particular point where now you do not have any unbalanced moments, and that is the deflected shape. And note that nowhere in moment distribution are we looking at the deflected shape. We are not interested in theta b and theta c. We are only interested in what the moments are at the ends, and that's what we are interested in. So the whole moment distribution process, it does this, and note that this will always converge. Okay, physically you can think about it, because what you are doing is you're starting here, this, then you do this. Now this is going to cause less, so it's going to need this. You're going to do this. Ultimately you're going to get a situation where you converge. So mathematically we can show that the gauss-seidel iterative procedure does converge, and because the gauss-seidel iterative procedure converges, the moment distribution procedure also converges. Now you never in moment distribution do you go till you get 0.0 and exact. What you do is typically you stop after 3 or 4 cycles, or till your unbalanced moments get less than 1% of the moments at the ends. Okay, and then you stop over there, and that's once you know the member and moments, you've solved the problem. Okay, the advantage of this method is that it is a completely algorithmic procedure based on distribution factors and carryover factors being computed, and then you keep computing unbalanced moments and constantly computing the net unbalanced moments, distribute it, carry it over. Again, look at net unbalanced moments, distribute it, carry it over. In this particular case, we are doing it, we are distributing B, then we are going to see distributing C, then we are going to be again distributing B, C, B, C, B, C. This is the physical procedure. We will see in the next lecture that we don't, this becomes a very cumbersome procedure. Ultimately what we have to see is that the unbalanced moment, we look at all the joints, look at all the unbalanced moments, distribute them, then carry over, then continue. So in other words, what you have is you have cycles one cycle where you distribute, then you carry over, then the next cycle again you distribute, then you carry over, then you distribute, carry over. Which is the last one? The last one is where you distribute so that you get balanced. You do not need to carry over because the moments are small enough so that carrying over will not have tremendous effect. Okay, so this is the procedure that we will look at. We will continue looking at this particular problem, and we will also see that the modifications, remember in the displacement method we had the fixed beam and then we had the fixed hinged modified member. Similarly, even in moment distribution you can actually have moment distribution for a modified member, and we will see all of these in the next lecture. Thank you very much.